All right, this is the last part for section A1. And in this, we're going to go ahead and review functions and function notation. This comes from section 1.3 in the textbook, pages 30 to 43. All right, so we've already talked a little bit about some of these things in the previous video. The first one was that we talked about a relation. Remember that a relation is just a set of ordered pairs. Anytime we state when x is this, y is that, you are using a mathematical relation. Remember that relations can be given using tables, equations, sets of points, and or graphs. Inside the relation, we have domain. This is the set of all inputs, or the x values. And we also have range, which is the set of all outputs, or y values. All right, so now we're going to go ahead and introduce the next concept related to this, which is function. And so function, this is a relation in which each input corresponds to only one output. So a couple things to notice when we talk about this. Input values appear at most once. So x values can only appear once. The output values, on the other hand, can appear single or multiple times. So functions, these are used to represent real-life scenarios. For instance, if we let the students be the inputs, and we want to know where they're traveling to for Thanksgiving, be the outputs. So here are kind of some ideas. Eric and Anna are inputs. Can they both go to Albuquerque? Sure they can. They can even take the same car. And so this is allowed. On the other hand, if we look at Stuart, can Stuart go to Los Angeles and New York City? Well, you could argue that he could go to Los Angeles and then catch a flight and then go to New York City, but he cannot be in these two places at the exact same time. The only person who can do that is Hermione Granger, and, well, that's magic, and we don't do that, okay? So this is kind of an example of functions and non-functions, okay? All right, so now we want to talk about notations for domain and range. Okay, so the first thing we have, we already looked at it in the previous video. If the relation is written using a table or a list of points, then we can write the domain or range as a list of values separated by commas inside squiggly brackets. So for instance, if we have values of -2, -1, 0, 1, and 2, then we just write those numbers inside squiggly brackets, separate them with commas. Now, on the other hand, if we have a relation that is given as an equation or graph of a continuous function, a continuous function means that basically we can draw it and, well, we can draw it as a line, we can draw it as all sorts of things. But the thing is that we don't just have a set of points, we have many, many points on this graph. And so we cannot list them all out. And so we can write the domain or range using set notation or interval notation. Examples of set notation, we can say things like x such that x is a real number. So set notation, these are going to be the basic things that we need for set notation. The first thing we need is we need our variable. So for instance, all of these are going to be examples of domain. We have our x, we have this little bar, and what this little bar translates to is such that. Mathematicians hate writing words. And then what we have is we have the condition. So for instance here, x is a real number. And then again, we have our squiggly brackets. We can also write these using interval notation, and one of the nice things about interval notation is we don't have to have the variables. So we don't have to keep track of whether it's x's or y's. So for instance, x is a real number. What that translates to is negative infinity to positive infinity. And we use parentheses on both ends to indicate that we cannot equal it. All right, other examples. We have another one. We have x such that x is greater than or equal to 4. When we write this in interval notation, we start at 4 and we want to go to the right, or we want all the numbers that are bigger. And so we are going to go to positive infinity. Because we do have an or equal to statement here, we are going to use a square bracket. And again, we cannot equal infinity, so we are going to use a parenthesis on that one. And finally, our last example, we can say what x is equal to, or we can also say what x is not equal to. So for instance, in this last example, we have x such that x is not equal to 3, which means that x can be anything except 3. When we write this in interval notation, what we do is we start off with our negative infinity to infinity, which is all real numbers. And in order to show that we don't want to include 3, we're going to go ahead and have negative infinity to positive 3. Notice here that we have parentheses on both ends because we cannot equal it. This symbol, we'll talk about it later a little bit more, but this is called the union symbol. And what this translates to is the word or. Again, mathematicians don't like words. And then what we do is we finish it off by saying or 3 to positive infinity, and again we have the parentheses around these two to indicate that we are not equaling it. All right, so those are examples of set notation and interval notation. You will see set notation in your math classes, but we do kind of prefer to use interval notation. It's a little easier on the eyes, and it's basically just a shorthand number line. All right, so now let's get into some other things that we want to know. When writing domain, we want to start with the smallest x value or x coordinate. This is the leftmost value for our domain. And we want to move to the right to the largest x value or coordinate, which is our rightmost value. And those are going to be the two things that we put inside our parentheses and or brackets. So domain, we are going from left to right, and we only care about x coordinates. When we talk about range we want to start with the smallest y value or y coordinate. This is going to be on the bottom. And we want to move to the largest y value or y coordinate, which is going to be the topmost point. If the end value is a solid point, that number should be inside square brackets. It is included. So solid points are included. If the end value is an open circle or an asymptote, we'll talk about these ones later, then it is not included, and we use a parenthesis. If the graph or equation extends on forever, we use infinity symbols. If we're going to the right or the top, it's a positive infinity. If we're going to the left or down, then it is a negative infinity. And these ones we always use parentheses. All right, that's our notation for domain and range. Okay, so then let's talk a little bit more about function notation. So functions, remember, functions means that each x we plug in results in just one y value. And so function notation, the first thing to note is it is just a notation. All it is telling us is that it denotes an equation or relation that is a function, meaning that each x corresponds to at most one y. So in our notation, we've talked about equations for many, many years now. To write it in function notation, we're just going to replace the output, usually the y variable, with the notation f of x. This is f parentheses x close parentheses, and this is read f of x. One thing to note, what this means is this means the function evaluated at x. It does not mean f times x. All right, so let's go ahead and see what we can do with this. So our basic notation is f of x equals y. This is kind of what we want to think about. So when we look at this, the numbers that are inside the parentheses are going to be x values or x coordinates. Notice that inside the parentheses, this is our x. The numbers that are on the other side of the sign are always the y values or the y coordinates. So let's go ahead and now look at some relations using equations with x's and y's and how they translate to function notation. So if we look at the equation y equals 3x, what we can do is we can rewrite this as a function because it is a function. Remember that all we do is we replace y with f of x. Now, when we work with equations, we have to go ahead and say things kind of very wordy. So for instance, when we work with the equation, we might be asked to find what is y when x is 2. And so in order to do this, what we do is we replace x with 2, and then we simplify. In function notation, we can translate this whole statement into find f of 2. Again, all this means is we want to plug 2 in for x, and if we plug it into the x in the parentheses, we need to plug it in wherever we see x in our expression. But it's the exact same thing. Now, we can also go the other direction. We can go ahead and say things like, what is x when y is 7? This one we'll talk a little bit more about it later because in function notation it is still kind of wordy. We say find x when f of x is equal to 7. So we take our 7 and we plug it in for the f of x. Just like over here, we plug in 7 for y, and then we find x. Okay, so the main thing to remember, if given a function statement, the number inside the parentheses represents the x-coordinate, and the number on the other side of the equal sign represents the y-coordinate. So for instance, f of 1, if I tell you f of 1 is equal to 2, what this means is when x is 1, y is negative 2. And remember, points are always x comma y. So this becomes, 1 becomes my x-coordinate, and negative 2 becomes my y-coordinate. And we can go the other direction as well. If we're told a point for negative 1 is on a point on a function, then what we can do is we can go ahead and write it in function notation. 4 is our x-coordinate, which means it goes inside the parentheses, and negative 1 is our y-coordinate, and so we put it on the other side of the equal sign. We are going to be playing around with going back and forth between these different notations, and the important thing to remember is just, they are just notations, okay? Do not get so hung up on what is what. The main thing to remember is, remember the basic definition for function, f of x equals y, and you can see exactly where everything is in this statement. Alright, so functions was something that was introduced in the previous math class, and this is a concept that you're going to see a lot in this semester and all of your future math classes. We are going to be going back and forth between the different notations. One of the benefits to using function notations is that we can use different letters to represent different equations. So for instance, in equation notation, if everything is in terms of y's and x's, not only do we have to be able to tell you what we're plugging in for, but we also have to tell you which equation, and it gets kind of wordy. Whereas when we talk about function notation, we can know which equation to look at by its definition. They're not all going to be f of x. We can have g of x, h of x, c of x, m of x. You can have any kind of letter in the front to differentiate between the different equations. And so when we do this, we look at the letter in front and we know exactly which equation we're plugging into. As mentioned earlier, functions are used to represent real-life scenarios. And over the course of this semester and future math classes, we will be looking at quite a few real-life situations and using functions to create equations as well as answering questions given either an input or an output. Alright, so let's go ahead and practice a little bit of this going back and forth between our different types of notations. We have a table here, and so the first thing that we want to do is we want to write each line in function notation. So here we have when x is negative 5, f of x is equal to 4. And so remember, our basic notation is f of x equals y. And so for each one of these, we have when x is negative 5, y is 4 in function notation. We have when x is negative 3, y is 1 in function notation. We have when x is 0, y is negative 1. And so we have f of 0 equals negative 1. And then finally, our last two, we have when x is 3, y is 1, so f of 3 equals 1. And last one, we have f of 5 equals 4. All right, we also want to write these as a set of ordered pairs. And so remember, ordered pairs are always x comma y. So we have -5, -3. Sorry, I'm doing this wrong. Okay, we're writing as points. So we have -5, 4. We have -3, 1. We have 0, -1. We have 3, 1. And we have 5, 4. All right, we want to list our domain and our range. So our domain is the x values. And because we have a list of points, we're just going to go ahead and put them inside the squiggly brackets with parentheses, or with commas separating them. For our range, again, it does not matter what order this is, but I have -1, 1, 4. And the important thing to note here is that any values that are repeated, for instance, I have 4 repeated and I have 1 repeated, we do not repeat them when we write our range out. We only report each number once. And so this is our range, and it covers all of them. Okay, that takes care of that one. The next thing that we want to do is we want to talk about different types of functions and their domain. These are going to be functions that we're going to see over the course of the entire semester. And so we're going to start with our basics and kind of work our way up the difficulty levels. The first one we have, we call it the constant function. And our constant function is just going to be a function. We have our function notation, so it is a function. And it is just going to equal a number. There are no x's, except for that one, in this equation. So for instance, f of x equals 15 is an example. Our domain, we can plug in whatever we want for x. And so our domain is all real numbers, or -infinity to +infinity. But our range is a single value. In order to write our range, this one, we cannot write it in interval notation. This one has to strictly be written in set notation. It is just k. All right, so what does this look like? If we graph this, just as an example, in order for y to equal some number, all the x's are going to be the same, but all the x's are going to be different, but our y is going to be the same. And what we get here is a horizontal line. So here, when x is 1, y is whatever this is. When x is 5, y is whatever this is. The same thing on the negative side. If x is -2, y is this number. And so it is just a horizontal line. This is still a function because we do not have any x values that go to different y values. All right, the next one we have is our linear function. Constant functions are technically linear functions, but they're kind of the boring examples. We're going to look at all the other linear functions now. And linear functions, what we have is we have a f of x equals mx plus b. This is our, we call it slope-intercept form. And so all linear functions can be written in this form. An example, 4x equals 3x minus 4. If we draw this, we all know kind of what a line looks like. And so what we have here is we can do a line that goes up from left to right. It can also go down from left to right, okay? But we do have that it is going up or down forever. Now, if we analyze kind of this graph a little bit, notice that my arrow goes forever to the left and forever to the right, which means that my domain is negative infinity to infinity. This goes forever left, forever right. And my range, what we have is that this goes forever up, and it goes forever down on either side. And so my range is also negative infinity to infinity. Okay, the next one that we have is the absolute value function. In the absolute value function, what we have is absolute value bars. And inside our absolute value, we have to have the x, but we can also have other things in here too. We can add numbers or subtract numbers on the inside and outside. We can also multiply, which we'll do later this semester. And so what we have here is for our absolute value function, our domain is all real numbers again. Okay? And that's the main thing we want to focus on here. Our range, we actually have to graph it in order to see what it looks like. And so just to give you an idea of what an absolute value function looks like, it is a V shape. So for instance, I can draw one here. You can also have one that goes down. And we'll talk about, okay, how do we do that? But the important thing is we have a V shape. This goes forever left and right. But notice that in order to find our range, we do have to find this bottom point or this top point and use the concept of does it open up or does it open down in order to find our range. All right, those are our first three. All right, let's look at some other ones. All right, the next ones that we're going to look at are special cases of polynomial functions. And so we have our quadratic function. This is one that we've seen for several semesters as well. And our general form is going to be f of x equals ax squared plus bx plus c. So an example is x squared minus 3x plus 2. So for this one, again, note we have our domain is all real numbers. We also have our range, and so in order to determine our range, we do need to know the vertex and whether this opens up or down. So just a reminder, when we graph this, what we have is a polynomial or a quadratic. It is a parabola that can open up, it can open down, and we can move this in our figure, but this is our basic shape. One of the things to note is even degree polynomials will also kind of have this setup, can get a little bit more complicated, but they also have domain of all real numbers. And again, for any of these even degree functions, and by even degree what I mean is that our largest exponent is even, we can go ahead and use kind of the same ideas. The next one we have is our cubic function. This one has a degree 3. And so for instance, a basic cubic function, x cubed minus 27. The cubic function has a domain of all real numbers. It also has a range of all real numbers. This is also going to apply to any odd degree function. So if our largest exponent is odd, then basically what we have is, and again, these can get kind of crazy, but a cubic function is going to look something like this. It can also look something like this. But what we have is it does go forever to the left or right, and it does go forever up and down. The next one that we've talked about a little bit in previous math classes is our rational function. Now, one of the things to note is so far all of the ones that we've talked about have domain of all real numbers. Rational function is the first one that we run across that does not have a domain of all real numbers. And our domain is going to be all real numbers except where the denominator is equal to 0. So for instance, on our example here, if x is -2, then this is undefined. We can never divide by 0. And so that's something that we've talked about in previous math classes. We've talked about the domain of rational functions. We have not talked about range. And so we will be talking about this semester. We will also be talking about graphs of rational functions this semester. Okay, that takes care of those. All right, some other ones that we have. We have radical functions. And so, for instance, a basic one is going to be a square root. And our square root functions, or our radical functions, we actually have two categories, and I forgot to include the second one on here. But when we talk about even roots, for instance, square roots, fourth roots, whatever, we have our domain is, we cannot take the square root of negative numbers. So to find the domain, we set the inside greater than or equal to 0. And we solve it. We haven't really talked about range previously, but we will be talking about that this semester. Now, in order to graph a square root function, we're basically going to look at something like this. Now, this is for an even function. So, for instance, if it's a square root, if it's a fourth root, if it's a sixth root, we're going to have something that looks like this. We do have other radical functions, and our other radical function is, for instance, a cube root. And so if we have a cube root, then what we do have is a domain of all real numbers. And we also have a range of all real numbers. And we're going to talk about this a little bit later, but kind of like our cubic functions or any of our odd functions, when we graph these, what we get is something that looks like a sideways snake. And so it does go up forever and down forever. It does go left or right forever. Exponential functions was something that was introduced last semester. And an exponential function is where instead of x raised to a number, what we have is a number raised to x. Exponential functions have two basic shapes. And what we have is it either goes up forever as we go to the right, or it can go look something like this. We do have a domain of all real numbers for both of them because they do go forever to the left and forever to the right. But our range is going to be 0 to infinity. And notice here, this is the first time that we see a number inside the parentheses. And so what we do is we get closer and closer to 0. We never actually touch it. The last one we have is logarithms. And logarithms, when we graph them, I'm just going to graph one of them. what we have is kind of the opposite of our exponential. We have a domain of 0 to infinity. Again, we have, this is in parentheses. We get closer and closer to 0, but we never actually touch it. And our range, we do have that this goes down forever, and this goes up forever. So those are the basic functions that we work with in this class, and you will see them again. And so we'll be playing around with these a lot. And we're going to kind of expand on some of these ideas in this course that we haven't seen previously. All right, so the next thing that I want to do is review a little bit about evaluating functions. And so let's go ahead and start with example A. We have f of x equals the square root of x plus 3. So remember that when we evaluate, what we want to do is we want to take whatever is inside the parentheses and we're going to replace it for the x's. And so if we evaluate f of 6, what we should get is this is equal to the square root of 6 plus 3. That's our plug-in step. And now we do want to go ahead and simplify this. So we simplify inside our square root, and we get 6 plus 3 is 9. And we can simplify the square root. Square root of 9 is equal to 3. All right, so now let's repeat the process, but we're going to plug in negative 19. And so if we, again, kind of the same idea, we want to take our negative 19 and we're going to plug it in for the x's. And if we plug this in, we get the square root of negative 19 plus 3, which is equal to the square root of negative 16. Now, for me, we have not talked about what we do with this yet. This is not a real number. Now, this particular textbook, they don't use this definition. What they do is they call this undefined. And so this is the one that you will want to use when you do your homework. All right. Now, not only can we plug in numbers, but we can plug in expressions. And so it's still the same concept. Here, inside our parentheses, we have a plus 5. And we want to do the same thing with this that we did with our numbers. So wherever we see an x, we're going to plug in a plus 5. And we want to simplify it as far as possible. So if we do this, we get the square root of, again, x we're going to replace with a plus 5. And then we still have our plus 3. In order to simplify this, all we can do is combine like terms inside. And so we want to add 5 plus 3. We'll leave the a alone, and we get a plus 8. We cannot simplify this any further, and so this is as far as we go. All right, now let's talk about the domain. Remember that square roots, we do have restrictions on our domain. And remember that what we want to do is we're going to take the entire inside, the x plus 3, and we want to set this greater than or equal to 0. It has to either be 0 or positive. Remember, we cannot take square roots of negative numbers. And so, in order to solve this, we subtract 3 from both sides. We get x's greater than or equal to negative 3. And remember that we have two different notations that we can use. If we want to write this in set notation, Remember that all we're going to do is we're going to have our squiggly brackets. We put our x and our bar, and then we just put this statement again. So we say x such that x is greater than or equal to -3. If we want to do interval notation, we start with our smallest value, and the smallest value that satisfies this statement is -3. -3 is the or equal to part, and all of the numbers bigger than that. We put a parenthesis around the infinity. And we're done. All right, let's look at a couple more. Okay, if we come to example B, let's start by evaluating for g of -4. So again, remember, we're going to plug in the -4 for x, and wherever we see an x, we replace it with a -4. And so when we do this, we get 15 plus 3 times -4, and we simplify using order of operations. We're going to multiply 3 and -4 becomes -12, and 15 minus 12 is 3. All right, again, we can do this using not only numbers but expressions. And so here we want to plug in our a-2 for x. And if we do this, we get that this is equal to 15 plus 3. And we want the a-2, just like the -4, we want the a-2 in parentheses. In order to simplify this, we want to distribute the 3. I'm going to bring down my 15. We multiply 3 times a, we get 3a. And we want to multiply 3 times -2, we get -6. We can combine our like terms, and our like terms is the 15 minus the 6. And so we are going to get 3a plus 9, or you can also write this as 9 plus 3a. All right, let's talk about our domain. Our domain for this is a linear function that has a slope. It's not a constant function, it's a linear function, which means that it does go forever to the left. I can plug in any numbers that are negative, and it goes forever to the right. We can plug in any numbers that are positive, and well, we can also plug in 0. All right, last example, we have h of x equals 2x minus 8 over x plus 5. So the first thing that we want to do is we're going to plug in -3 for x, which means that I want to replace all x's in my expression with -3. X can occur multiple times, and we can plug in the number multiple times. So if we go ahead and plug this in, we get 2 times -3 minus 8 in the top, and in the bottom, we get -3 plus 5. We can simplify this. If we multiply in the top, we get -6 minus 8. And then if we go ahead and do our addings and subtractings, or our combinings, -6 and -8, they have same signs, so this is going to be -14. -3 plus 5, we have different signs, so it's going to be +2. And we can simplify this down to -7. And that is our final answer. All right, if we plug in, same idea, if we plug in -5, we get 2 times negative 5 minus 8 over negative 5 plus 5. In the top, if we simplify, we get negative 10 minus 8, which is negative 18. And if we combine on the bottom, we get 0. But one of the things to remember is we are never allowed to divide by 0. This is undefined. All right, last thing that we want to look at is our domain. So remember, fractions, we do have trouble spots, and our trouble spot is when the denominator is equal to 0. Well, we already know what the trouble spot is with this last example, but if we go ahead and actually find it from scratch, what we do is we go ahead and set our denominator equal to 0, and we solve. So we can subtract 5 from both sides, and we get x is equal to negative 5. Now remember, this is the undefined spot, and so what we do is we say x is not equal to negative 5. If we do this in set notation, well, we want our x, we want our squiggly brackets, we want that bar, and then we just say x is not equal to negative 5. Now, if we want to write this in interval notation, what we're going to do is we're going to start at the very left. We have negative infinity. We can go all the way up to, but not including negative 5 because it's not equal to, which means that we put a parenthesis. We do want to kind of skip over negative 5, so we're going to put a union symbol or the or symbol, and then we pick up again at negative 5, again not included, and we go towards positive infinity. All right, those are some examples of evaluating and some examples of domain. All right, the next thing that we want to look at is we're going to look at some graphs, and we want to, again, we're going to do some evaluating, and then we're also going to go ahead and do some domains and ranges. Okay, so let's start with example A. And so example A, what we have is we're going to start with our domain and range. So remember that domain is the x coordinates. And so we want to find our leftmost x coordinate and then our rightmost x coordinate. So going from left to right, our graph starts right here. This is negative 2. Because it is a closed circle, we are going to use a square bracket. Our graph, and we don't care what it does up or down, but our graph continues. So every time that we move here, we are on the graph. Again, we don't care what the y's do, but we want to come over to this far right point. And this far right point has an x-coordinate of positive 2. It also has it's also included, it's a solid circle, and so we do want a square bracket. For our range we want to go bottom to top. So we're going to kind of start here, and the lowest point that I have is right about here. And I'm going to say that that looks like negative 3. And so the question is it included or not? And here it is included. It's not an open circle, and it actually does come down and touch the negative 3. If we continue up, as soon as I get to this point, I don't go any higher than this. And so this is going to be my highest coordinate. And it is going to, we want the y value because we are talking range. And so my range goes up to positive 3. It is included, and so we use a square bracket. All right, now, if we want to evaluate the function, remember that these numbers inside the parentheses are going to be the x's. And so when we evaluate this, I want a point that has an x coordinate of 0. If we come to where x is 0, that's going to be on our y-axis right here. And so we are looking at this point. We're looking at the origin. And so when x is 0, y is 0. And so to write that in function notation, we just say f of 0 equals 0. For f of negative 2, again, our negative 2, this is an x coordinate. And so I want to find the point that has an x coordinate of negative 2. X is negative 2 is going to be right here. And the y coordinate of that point is 0. And we're done. All right, let's come down and look at a couple other examples. Let's come down to example B. Example B, we have, again, we want to know our domain and our range. This one we do have to be a little bit more careful because if you notice we have these arrows on the ends of our graph. What this means is that these arrows do two things usually. We want to think about them in terms of x's when we talk about our domains. So when I look at this arrow on the left side, it keeps going to the left. And so this goes towards negative infinity. Remember, infinities, we always have parentheses. And if we come over to the far right of our graph, this arrow continues to the right forever, and so it goes towards positive infinity. Now we also want to think about these arrows from our range perspective. And so from our range perspective, this arrow on the left goes forever down. And so it goes towards negative infinity. This arrow on the right goes forever up. And so it goes towards positive infinity. All right, that is our domain and range. And the last thing we want is we want to evaluate the function. So we have f of 1, which means that we are looking for the point that has an x coordinate of 1. So if we come over to where x is 1, we find where it touches the graph. It touches our graph up here, and so we get f of 1 is equal to 2. We will be playing around with these graphs quite a bit in this class, and so we do want to make sure that we understand kind of the basics of some of these things, including our domain, our range, and evaluating. All right, let's go ahead and we got one more slide. We're going to look at one more example. Okay, example C. We want to start by finding our domain. And so the first thing that we want to do is we want to know, okay, how far to the left does this go? Well, if we look at the left part of our graph, we do have this arrow. And just a reminder, this arrow does keep going forever to the left. And so we do have a domain that starts at negative infinity with a parenthesis. And if we trace our graph to the right, we're still going to the right, to the right, to the right, and we stop. we stop at x equals 2. And so on the far right, we have a 2. It is a closed circle, which means square bracket. And we're done with that one. Okay, we want to talk about our range. And so again, bottom to top. So bottom, we have this arrow on the left side that keeps going down. And so this is going towards negative infinity. Now, how far up does this go? Well, when we look at how far up this goes, we're going up, 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 and here we reach the top. We do turn around, but remember that with range, we only care about how far up. We don't really care about left and right, but we go up to this point. This point has a y-coordinate of 3. It is included, and so we do want to use a bracket. Okay, then we have our evaluate. Okay, f of 0, we have 0 inside our parentheses is our x-coordinate. So we are going to find where x is 0, and we're going to go up to where it touches the graph, and we get 3. All right, we also want f of negative 2. So remember that negative 2 is an x value. We are going to come across to where x is negative 2. And if we come across to where x is negative 2, we're going to go down our graph, and we end up right here. And so when x is negative 2, y is negative 1. And so f of negative 2 is negative 1. All right, that finishes up this section. That finishes up everything for A1. And again, this is kind of just a review, but these are topics, especially in this presentation. These are topics that we're going to continue to look at in terms of analyzing equations and graphs throughout the rest of the semester. And these are things that you will be looking at in all of your future math classes.